todo listo. Ya. ¿Ready? ¿Apariciones, amigo?
No aparece.
No aparece. 3 y 2.
Y ya está. Ay, ¿será que él estuvo conectado a las 2:30?
Profesor Macari.
Porque decía que era a las 3.
¿Dónde?
Sí, o sea, alguien dijo que era a las 3. Sí. Creo que hoy.
Sí, pero no le dijo eso. Bueno,
Oiga, dijo que era a
pero
las 3.
en el informe.
So we have to start. Okay. Today we have a presentation by our invited professor Michael Owen from Virginia Tech University in the United States. Well, Michael, it's the first time here with us, but we met in other events like Rio de Janeiro, Laciam, and previously in another event in the United States. So Michael has been working on mosquito, mostly with people from Argentina, but now the idea is to extend this to Colombia too. So Michael will talk about the old strength in a new region. So this is about dengue. Michael, the stage is yours. Please go ahead.
Thank you, gracias.
They don't know me in English.
Gracias, Olga, y gracias a todos por asistir hoy. Mi primera vez en Cali. Tenía una semana muy buena esta semana. Porque en español es solo así, voy a hablar en inglés, pero si tienes preguntas, por favor, levanta tu mano para trabajar. Voy a explicar. So I will switch to English now. For English time. So I am going to talk, just to say again, thank you to Olga for inviting me. Thank you all for coming. I am going to talk about a project I have been working on in pieces for a very long time. And the focus of the project has recently been on work in Argentina. Before I say much, I want to say that this project has been a very collaborative project. So the things I'm going to talk about today, all of these people that are pictured here, and all of these people that are named here, because I ran out of room for pictures, have been involved in this project. So I won't talk about everyone here, but the main collaborator is Elizabeth Estajo, who is at CONICET, based in Argentina, and her team, which includes all of these people, and our collaborators from the Inter-American Institute for Global Change Research in Montevideo, collaborator from Cambridge. These are collaborators from the Dominican Republic who contributed some to this project. These are my two PhD students, Morgan and Sala, who have been working on parts of this project, and then my former postdoc advisor and our collaborator. So, a lot of people from a lot of different backgrounds. These are biologists, ecologists, doctors, geography, statisticians, virologists. There's a lot of people involved in this project. You don't really have to tell this group that mosquito-borne diseases are a problem. In particular, malaria and dengue are the top two mosquito-borne diseases across the globe. And I'm going to focus this talk entirely on dengue, which causes anywhere from, I've seen estimates from 96 million up to about 450 million cases every year. This year has been a particularly bad year for dengue in the Americas, as I'm sure you all know. This is a disease that's transmitted primarily by Aedes aegypti mosquitoes. And it's largely a disease that's centered around the equator, the equatorial regions, in tropical, subtropical climates primarily. But it is spreading, or south and farther north. This is dengue in Colombia over the last, what was that, 30, 40 years, from 1980 up until, this is where we were this year at the time that I printed this, or saved this last night. So Colombia obviously has had dengue for a while. The vector of dengue is Aedes aegypti. It's this mosquito that really loves to feed on humans, prefers to feed on humans, in fact, and lives in these artificial containers, so buckets, pots, tires, artificial water. That's where it really likes to lay its eggs and breed. Aedes aegypti is a very good vector. It vectors dengue, Zika, chikungunya, yellow fever, Mayaro. So it's a very good vector of human diseases. The mosquito is also very much concentrated in these tropical regions. I typically have this here for my US audience, but it's also in parts of Southeast United States. So the idea being that theoretically anywhere we have this mosquito, there is a risk of having dengue eventually. Dengue has spread quite a lot since 1980. So back in the 80s, there was dengue in a few countries. In the 70s, it was only in 9 countries, and then it has spread to more and more places across the globe and now this figure is unfortunately about 10 years old. It's still the best one I can find. It was in about 128 countries in 2013. I'm going to focus in now from the global dengue problem to the region, the Americas. So just to put this in context, these are the cases of dengue in the region that is defined as the Americas at large. So North America, South America, basically everywhere in this figure. This is what we have been seeing in 2024. These are the dengue cases that we have had. This is what dengue looked like last year. And this yellow curve is the 5-year average of dengue for the previous years from 2022 back. I include this to emphasize that this year is a very bad year for dengue. And in fact, in most places, it is the worst year that we have had of dengue yet. There were some places that said that last year too. So for instance, Argentina had its worst year ever last year. It's having its worst year ever this year. Before that, the biggest sort of outbreak we had was in 2019, where dengue was really bad across the Americas as well. To zoom in more, I'm going to think a lot about Argentina, which is part of the southern cone. And this is the situation in the southern cone, so the shape is very similar. One thing you might notice, if you just look at the scale here, this is 640,000, this is 700,000. So most of these cases that we've had in South America this year have been in the southern cone region. And this is important. Sorry? Because Brazil, because Argentina is having a very bad outbreak this year too, so a lot of those cases are in Argentina and Brazil. Chile has no cases as far as we know, so it's not even involved. And Uruguay has very few cases, so it's largely these two countries. Obviously Paraguay is in there as well. But, yeah, so it's, Paraguay has also had a lot of cases, but it's interesting to see that most of this big outbreak we're having is being driven by South America. One other thing to say here, in 2023, Argentina and Brazil also had a big chikungunya outbreak, and that was the first sort of big outbreak for that region for chikungunya as well. And so this also happened alongside dengue, which was interesting. In Argentina, so zooming in some more, dengue was largely, well, so dengue first sort of showed up in the northern provinces in the late 1990s. And until 2008, the only dengue in Argentina happened in these provinces up here. In 2009, there was a much bigger spread of dengue throughout the country. 2016, it was worse. 2020, it was all the way down to the central region. Since, I think in this most recent outbreak, there have been some cases sort of in this region as well, so this is sort of the new southernmost point of dengue in the southern hemisphere, as far as we know. So this also seems to be getting worse and worse. And this study that we did is now 4 years old, so we need to update it. In central Argentina, so this is where I'm going to focus most of the rest of the talk, is in this province near Córdoba, and in particular the city of Córdoba. This is a temperate region, so it's not tropical at all. They have pretty mild winters. They have pretty warm summers, but not too hot. And they tend to get most of their rain in the summer. This was the first outbreak in Córdoba in 2009. And as you can see, sort of with each outbreak we've had, it's just getting worse and worse. And in fact, this is as of early March 2024. So this isn't even up to date. Of course, I'm sure everyone is aware that Argentina is also having a lot of political issues currently. I don't know why the data they have available has not been updated in 2 months. I suspect it has something to do with the current political situation. But the important thing, well, one of the most important things is this was not that long ago, right? This was 2009, and this is where we are now. So it's gotten a lot worse very quickly. This is something that has been in the news in both the US and Europe, as well as, of course, South America and Latin America in general. This is what is being called the worst outbreak of dengue to date for the entire region. Argentina, in particular, has made a lot of news for running out of repellent, not having any bug spray. They also, I don't think I didn't include this up here, but they've also started rolling out the sort of suboptimal dengue vaccine in Argentina as well, trying to get people vaccinated. But there's a lot of issues with that particular vaccine, because in order to get the vaccine, you have to have had dengue once already. And I should say, this is actually an article that was written about Elizabeth Estayo, my collaborator, and her group there. So we're very proud of that article. Okay, so I'm gonna spend the rest of the talk talking about two particular sort of big questions. How can these models help us better understand why we're seeing so much more dengue so quickly? So what I'm calling dengue emergence in the region. And how can we improve these predictive models and develop early warning systems to help predict outbreaks so that we can work with local vector control and public health to sort of help them prepare for these. There are a lot of drivers of dengue spread. Urbanization is a really big one. In general, more people are living in cities than are living in rural areas. So that makes it very easy for dengue to spread. This is obviously a very big one that we saw as one of the main drivers of COVID. In fact, people are traveling a lot more quickly. It's very easy to get from one part of the world to the other part of the world within the incubation period of these viruses. Climate change is where I spend most of my time thinking, so that's where I'm going to spend the rest of the talk. And then there's also things like the development of insecticide resistance, which is making control efforts a lot harder. There are a lot of reasons that we can link dengue and temperature. So I'm even going to focus more on temperature than climate as a whole. For the moment, I have some comments about that at the end. But in terms of temperature, these very warm areas are these same areas where we see dengue and the same areas where we see I like to sort of stop here and say, I know this is not the only reason that we have dengue and the mosquito in these regions. It's not just about temperature. A lot of these areas, the sort of socioeconomic conditions are a lot different. Housing is a lot different. There's also other environmental variables like precipitation, humidity. So there's a lot of contributions to why we see dengue in these warm areas. I'm going to focus on temperature. So these are a few different relationships between temperature and traits that we're interested in. Obviously there's a lot of information here, so I'm not going to go through everything, but this is a paper by Aaron Mordecai and her group back from 2017. This work, I feel, has some issues, so I don't necessarily like the way they fit all of these curves, but it's the one place where you can sort of get all of this data in one paper and be able to kind of know that you're using the same methodology to characterize these relationships. And so, for instance, in terms of adult vector lifespan, we see sort of optimal temperatures around 25 degrees Celsius. Something similar for egg to adult survival. These are related to the mosquito life cycle, but there's also things that are related to transmission. So generally, as it gets a little warmer, transmission seems to happen more often. And incubation. So the virus incubates in the mosquito, and that tends to happen faster as it gets warmer. So there's all these relationships between temperature and mosquito life history characteristics and disease transmission that are very important. And so one big question is, how do all of these things work together to create different risk levels for dengue transmission? This is just a very general life cycle. So the 80-digit life cycle goes through egg, larvae, pupae, adult. For the models that I'm going to talk about today, we focus on temperature in the adult vector lifespan and in the larval development time. The reason for that is at the time that I started on this work, those were the places where we had the best data. So the relationships that I'm going to use come from a couple of older papers. Well, this one's not so old, this one's older. And basically we took a meta-analysis and fit a quadratic curve to the adult vector lifespan. And then these are the development rates of all of the stages of larvae. And as you can see, in general, as things get warmer, that development time is much faster. There's also some things in terms of the transmission cycle that are temperature dependent. So this is a general transmission cycle. So for dengue, there's only sort of mosquito to human transmission, right? There's no mosquito to mosquito or human to human transmission. When the virus is in the mosquito, there's an incubation period that it turns out is very susceptible to fluctuations in temperature. So that's where we're going to focus on including temperature for the model for now. This comes from a study that my colleague Rebecca Christopherson did. This is basically the data that she gave us, and then we did some sort of bootstrapping on that, and we're able to calculate these average incubation periods for different temperatures, and we fit a curve to that. We realized we fit an exponential curve to 3 data points. It was very hard to get those 3 data points, so we have stuck with this for now, but we are looking at ways of doing something a little more robust with this. So that's a little bit of the background on why we care about dengue and temperature. Now I want to talk about some of the initial, more statistical work that we did with dengue climate, primarily in Argentina, but also in the Dominican Republic. So I showed you these figures earlier. This is just the spread of dengue in Argentina over the last 25 years. These are maps, and you probably can't see the numbers too well in here, but if you just focus on the colors, these are maps that show the differences in mean temperature, minimum temperature, and maximum temperature for the past 20 years versus the past 60 years. So these are basically, the way that we can interpret these is the red areas here are places that have gotten warmer, and then the darker it is, the more warmer they have gotten in the last 20 years. And the bluer areas are places that have actually are a little cooler than they used to be. And so I focus basically on this minimum temperature metric here. You can see, at least in these areas here, things have gotten a lot warmer. And then there's spots down here in the central region. Córdoba is sort of in this region here, but this region has been quite a bit warmer, and this region has been quite a bit warmer as well. And so one thing that we were able to say out of this paper is that there seem to be some relationships here between the way that dengue has been spreading and some of these regions that are getting warmer. I think these areas down here, even though they're warmer, they're still a little cool from like this region, sort of, yeah, this region to the south. But there are places that, as they get warmer, are places that we need to watch because they could be at risk of having dengue. Precipitation is a little bit more complicated, right? So with precipitation, we have these places that are losing. So in blue here are places that are actually getting drier, having less precipitation. And in red are places that are having more precipitation. Precipitation and dengue is difficult because in a lot of these places, especially sort of in these more kind of rural areas up here, when there's not enough rain, people tend to store water, which attracts the mosquitoes. And then when there's a lot of rain, then there's a lot of rain in different places for the mosquitoes. And the other thing that can happen is if there's too much rain, then the mosquitoes get washed out. So the relationship between precipitation and mosquitoes and dengue is very complicated, unfortunately. But we looked at the relationships we have. We're still thinking about precipitation. So that was an analysis just looking at trends in climate and trends in dengue. This was for Córdoba in particular, where we did a correlated lags analysis, where we looked for relationships and timing between relationships between climate variables and mosquito variables and dengue variables. And the two things that showed up to be most significant were we had a positive correlation between the mean temperature and the number of eggs that we saw in the traps that were there. And that correlation happened at 0 months, so the interpretation there is that the minimum temperatures at the current time contribute positively to the number of eggs at the current time. And then we found a relationship between minimum temperature and the percent of neighborhoods that were positive for mosquitoes. So, and that was also at 0 months. There are some issues with this analysis, I think. One issue is that what happened is when we started this project, we were given a lot of data for mosquitoes, ovitraps, so eggs, dengue, and I think also some adult numbers from different neighborhoods. And it was all on different timescales. It was, some of the data didn't overlap, so we had to take the part of the data that overlapped, which I think was about 4 years, and we had to aggregate everything on a monthly timescale. So I think one reason that we see things like this 0 months relationship is because, at least in terms of temperature in eggs, you might expect that relationship to be less than a month. And so our lags are showing up as 0 months. We are working currently, and I'll talk more about this later, but we are working to create a much better data set where we are collecting egg data in particular, as well as climate data, and we are intending to revisit this analysis soon. But I do want to say that there are some relationships here between temperature and these mosquito populations, which is kind of the important part. We also did sort of analysis of trends, and this really didn't come up significant, but we did see a few trends here. So this is the minimum temperature deviation from the monthly average in Córdoba. And so there are certainly some places here where these peaks in temperature that are very far from the average tend to precede these outbreaks that we're seeing. Again, this analysis was done prior to 2020, so we don't have the most recent outbreaks included. But there are some relationships here, and I didn't include it here, but we also saw some similar relationships between differences in precipitation and dengue outbreaks as well. So this is something that we are continuing to look at, but there does seem to be an additional relationship there. This is something, and I was lucky to talk to Mauricio earlier about similar work that was done in Colombia that someone who worked on. But this was an analysis of many different temperature, precipitation, and humidity variables and dengue cases between 2014 and 2019 in 9 provinces in the Dominican Republic. And so I put this here in part to say that this is a set of relationships. These relationships between temperature and dengue are things that we're seeing not only in these emerging regions, but we're seeing them in these endemic regions as well. Dengue has been in the Dominican Republic for at least 30 years, and it just continues to get worse and worse. But we did see some relationships here between, for instance, the maximum weekly temperature. I didn't highlight them, but there's also some relationships that are a little less strong between minimum weekly temperature and mean daily temperature in these different provinces. And the most interesting thing is that we actually saw a lot of relationships there between humidity and dengue. And that is, obviously, humidity is related to temperature in some ways. And so there are some relationships there. The kind of interesting thing here, which it sounds like was the case for Colombia as well, or for Cali at least, was that we didn't see very many strong relationships between precipitation and dengue, which I think is interesting, but I'm glad to know that that's a result that has been repeated for other places that we would expect to see an effect of temperature. So now I have my big questions, but I've reframed them a little bit for climate. So I should say I'm thinking about these questions about prediction and understanding drivers for a lot of different factors. So not just climate, but I've been very, very interested in climate. And so the first question is, how can we actually think about including all of these climate variables in our models to better understand why climate is contributing to emergence? And can we make use of climate data, which for many places is generated on a daily basis and is available on a daily to weekly basis? So if we can use that data to help make predictions about what's going to happen with dengue, that would be, I think, very useful. And this is something that people have had some success with in other regions. But it's something that has been less studied in these regions where emergence is happening. So, these are my sort of 3 more specific questions. I'm not just interested in temperature. Because I'm working in temperate areas, I'm interested in how seasonality and temperature plays a role. And so how do these changes in temperature that we see in temperate areas impact what I will call sort of a window of risk or period of risk for dengue? How do we use this information to help us think about climate change? And then the third question, which I decided to take out of the talk, but I left the question here, is how do we decide sort of what's most important to include in our models? And I do have those slides if people are interested. I just wanted to try to cut this down to at least 15 minutes. So I'm going to focus on these top 2 questions, and then if there's time, we can talk about the third one. So let's start here with seasonality. And this is work that actually originally began 8 years ago, which I don't like thinking about, with my postdoc advisor, Helen Waring, and our collaborator, who's a virologist, Becky Christopherson. And you'll notice this is for US cities. I'll explain that in a moment. But this is a math talk. I thought we should talk about some math. So the model that I have is a deterministic model. It is a typical host vector epidemiological model that is described by ordinary differential equations. There are, in the base model, 7 equations for infection. So I don't think I have to go into detail with this audience, but we have our susceptible, exposed, and infectious vectors, our susceptible, exposed, infectious, and recovered humans. For what I'm doing, I'm thinking about one strain of dengue in sort of one year period of time. So we're not thinking about multiple types of dengue here, although that is something I do want to think about. Because we are interested in how temperature impacts mosquito population dynamics, we then also include these juvenile population dynamics for the larval stages and the pupae stage of the mosquito. So now we have 12 equations in our model for the vector population, the human population, and the different infection stages. Everything that you see here in what appears to be red or orange is things that I allow to be controlled by temperature. So now we have this non-autonomous behavior in the model where each one of these arrows, so all of the development rates, all of the survival rates, and this transmission or time spent in the incubation period and movement out of that, all of these things are controlled by temperature, which is then allowed to vary with time. These are the equations. Again, these are quite familiar, I think, to this audience, so I won't spend much time here, but the way that we incorporate some of these temperature variables is, so for instance, we have these are for the vector, the mosquito. So we have the emergence of the juveniles into the adult stage. And this is controlled by this rate nu here, which is a function now of temperature. And so this rate comes from this figure for each one of these transitions from the juvenile stages and from the final juvenile stage to the adult stage. So we can think about this value here as just being 1 over this image here, the inverse of that image. This, at least for the model I'm going to talk about for most of the time, is not controlled by temperature, although I will note that we can certainly think about controlling this alpha value is a function of temperature, or can be a function of temperature. But that's just the infection rate from susceptible to exposed. And then the mosquitoes spend some time in the exposed class, and the amount of time they spend in here is based on this temperature-dependent curve. And so again, this rho value here comes from taking the inverse of this figure that we see. And then the same thing with mortality. So all the mortality rates are controlled by temperature. This is the average adult vector lifespan, so we take the inverse of that, and that gives us the rate of mortality. So that's where all of the temperature-dependent variables come into the model. And we allow temperature itself to be controlled by this very nice, well-behaved cosine function where we can take the average value of the temperature across the year, the amplitude in the temperature, and of course this tau value allows us to sort of adjust for the peak of the temperature.
Can you go to the previous slide, please? Are the temperatures here the present, the current?
Yes, so the temperatures here are going to be the temperatures at the current time. And we take them, for what I talked about initially at least, we are taking the parameters here to fit a curve where the temperatures are the average of a 30-year period. But yeah, it's the temperature at like this moment right now. So we fit this model to temperature to mean temperature data for 30 years, and it determines the daily temperature in the model, which then feeds in all of those other parameters. I will say here, we did something similar with daily temperature range, so looking at how the temperature varies across a day. Which one, that data is a little less reliable. Two, it creates some issues with the model. I do have those results, and those results are in the paper, but I don't talk about them quite as much. But I think they are interesting and useful, because in some places where the mean temperature is, say, like 25 degrees Celsius, which would be like an optimal time, optimal temperature, those fluctuations can be between, like 35 degrees Celsius and 20 degrees Celsius, depending on where you are. And so those daily temperature ranges, I think, are important. Modeling them is less easy, less straightforward. So let's talk a little bit about modeling emergence. And so we did this initially with 6 cities in the United States that are all in regions where we might have a mosquito. We chose these particular 6 cities based on the differences in their yearly temperature profile. So this is the function that I showed you fit to 30-year data for each of these 6 cities. And we have places like San Juan and Miami that are very tropical. Miami a little more subtropical, right? So they have slightly cooler winters, but not that cool. And then we have places like El Paso and Atlanta and New Orleans that have these very cool winters, or more cool winters in the case of New Orleans, and warmer summers. So there's a lot of variation between the minimum for the year and the maximum. There is some reason for us to be concerned about dengue in the U.S. So this is from 2010 to 2020 of different outbreaks in the U.S. Of course, Puerto Rico is a pretty subtropical climate and has had some very big outbreaks in the past. Hawaii, which is also a very tropical place, has had outbreaks, but the slightly more concerning regions here are Florida and Texas, where Florida in particular is very subtropical, but is starting to see more and more outbreaks of dengue. So the first one that was really reported was back in 2010 in the Florida Keys. Most of these other outbreaks have occurred in Miami or the Miami area. And in particular, the number of cases that we saw in 2023 was 173, which doesn't sound like much, but for Florida is actually quite a lot. And I would say probably about 150 or more of these were concentrated around Miami. Texas has had some outbreaks mostly across the border with Mexico that have occurred a few times, the most recent one in 2020 that sort of coincided with the COVID-19 outbreak. So when we get ready to look at temperature and the effects of temperature, I have a lot of very colorful figures I'm about to show you. So this is just the temperature map over here of all the different places. This is the incubation period across the same time period that we see for the temperature here. So this gives us an idea of how the incubation period or the average incubation period is changing across a year. So for instance, if we look at this red curve, this is San Juan. And San Juan is very warm, above 25 degrees Celsius for the entire year on average. And the incubation period is somewhere around 8 to 10 days for the entire year. So very warm, very short incubation period. Miami, even though in terms of the temperature here, because we have that kind of exponential relationship between temperature and the incubation period, Miami, which is cooler in the winter months, but about as hot as San Juan during summer months, has these periods where the incubation period is actually quite long. So up to about 30 days in February, but around 8 days during the summer. There's a lot of changes in the incubation period across the year. Other places where we have a more temperate climate, so I'm probably not going to talk about this purple curve again. This is Los Angeles, and basically the result of our study was it doesn't really matter for dengue right now. It doesn't seem like it's going to be a problem. But some of these other places like New Orleans and El Paso in particular, so the yellow and green curves here, we have these periods where basically the incubation period is very, very long, but then we have this sort of window or this period here between, say, May and August, where that incubation period is very, very short. And so that's something that I think is interesting to think about. And one reason that can be interesting to think about is if we look at the lifespan of the mosquitoes. So for instance, here in Miami and San Juan, the lifespan is 25 days, pretty much on average, year-round. But in these other places, the lifespan can be quite short, around 10 days in the coolest months on average. And when we think about the relationship between these two figures, one thing that we have a question about is, can the mosquito survive the incubation period? And so we have this measure here of the probability of surviving the extrinsic incubation period, where, for instance, this value is very high, right, for San Juan year-round. That's because the lifespan is 25 days, the incubation period is about 10 days, so the probability that they survive is very high. But in other places, it's a lot more interesting. For instance, like New Orleans here, that probability of surviving the lifespan is basically zero, or sorry, surviving the incubation period is basically zero in the coldest months, because this incubation period is literally off the chart here. It's so high that we just cut it off. But the lifespan is 20 to 25 days. And then we have these periods here where actually that probability of surviving the lifespan is basically the same as it is in San Juan and in Miami. And that's because the mosquito is living for a very long time, and the incubation period is very short. So we have a much higher risk of transmission during that time. So this was the first sort of, I think, interesting result that we had from this work, where we started looking at how temperature affects lifespan and incubation period, and how those fluctuations across the year create different sort of periods of risk for dengue transmission. And again, like Los Angeles is kind of down here, just kind of ignore it. So then, I'm going to spend some time explaining this figure, but we then tried to look at the potential for outbreaks in the United States following an introduction in each one of these cities. So we considered a subpopulation of each city that was the same size, so that we could take out the effect of population size. And we introduced one infectious person, and we calculated the total number of cases that happened after that person showed up. So the way to read this is, someone showed up in March, and in San Juan, for instance, there were 1,000 cases that occurred, or sorry, 100 cases that occurred after that. It's not really the basic
But
reproduction.
it accumulates states.
Yeah, the cumulative sentence. Yeah.
Calculate not from the first infection, but chain.
Yeah, from all of the infections. Yeah. Yeah. So we were just trying to get a sense of how the timing when somebody shows up impacts the outbreak size. And we compared all of these cases together. I've drawn this black line here basically to indicate where like one case occurs. Yeah. And so if anything below this line, we just assume that there was no real outbreak. And anything above it, there was an outbreak of various sizes. I do have some very new work from the stochastic model to show you towards the end, but because obviously this is a deterministic model and there are issues. So one thing here is that basically it doesn't matter when you show up in San Juan with dengue, an outbreak is likely to occur after someone with dengue shows up based on temperature, which aligns well with what we see in the data from San Juan. So the outbreaks there's not really any particular periodicity, they just happen. The peaks are at different times, so yeah. And with Miami, we have what I will now start calling a window of risk or a period of risk between around February and August, where when somebody shows up in that period of time, there's a higher chance that they will lead, or that an outbreak will happen after they show up. And keep in mind, this seems maybe a little early here, right, in February, but if we think about the time it takes from an initial case to a secondary case, and you have to go through the incubation period, the infectious period, another mosquito, another infectious period, so a lot of time can happen between an introduction and a first case. And so this actually tends to align with the time at which things are starting to get more favorable. So the lifespan is going up. Yeah. So, right, this is sort of the very bottom. The lifespan is going up, the incubation period is going down, and that's what's driving what we're seeing. So that was our sort of major result, looking at how these different climate patterns can impact the potential for transmission. One thing that I didn't mention here is that currently we have not seen any reported dengue in New Orleans, which personally I find fascinating because it's like a swampland. And it's very hot, it's very humid. But this model seems to suggest that there is a period here in sort of April to August where we could see transmission. So any questions about this figure? Because I'm going to show you some more of these. I know there's a lot here. So the next question is, how do we use this model to ask questions about climate change? So we started off by taking a very basic approach to thinking about climate change. So if you think about that function that I showed you with the M1 plus the cosine term, what we've done here is we've just increased that average temperature, or that M1 value, by 0.51 and 1.5 degrees Celsius. At the time we wrote this paper, that was sort of the upper limit of what the Inter-Governmental Panel on Climate Change suggested would be sort of the 50 to 100 year increase in temperature. It's changed, unfortunately. But we're looking at 0.51 and 1.5 degrees Celsius. And so for these, I'll start with sort of the less exciting results. For places like El Paso, Atlanta, and Los Angeles, we do see some increases in the number of cases that we might expect. El Paso is maybe a little troubling here because we go from a period of a window of risk of just a few months for small outbreaks versus a slightly larger window of risk, but the outbreaks that do occur are much larger. But I think this row here has some more interesting results. So the solid line is the current situation. If we increase temperatures by 0.5 degrees Celsius, we see an increase in cases, but the window of risk really hasn't changed much. And then we start to see these kind of diminishing effects here, because what's happening here is that we are reaching and going past that sort of maximum optimal temperature for the mosquito. So it's getting too warm, basically. That's something that a lot of studies that have looked at mosquito-borne disease in the tropics have shown that actually in a lot of places it's highly likely that the mosquito situation is going to get better because it's going to get too warm for the mosquitoes, unless of course they adapt, which they're very good at adapting. In Miami, this is sort of the one I like to sort of talk about the most, because we have currently this very, not really short, but distinct window of risk from February to May. When we increase things by a half degree, that sort of period doesn't change very much. We include January. The number of cases does go up. But once we go up by just 1 degree Celsius, we have the situation here where we've gone from a few months of a risk period to the whole year being a risk period. So what I think is important here is that Miami seems to be sitting maybe just below the threshold for having sort of year-round likelihood of dengue outbreaks. So in terms of temperature.
Temperature is up 1.5 degrees year-round mainly.
Yeah.
Yes. And
Yeah.
even 1 degree plus will also give you kind of persistence of infection.
Yeah. Yeah. With New Orleans, this window does get bigger. So notice here it's basically April, May, June, July, and then it becomes February and August, and those outbreaks also get potentially quite a bit bigger. So this is just with thinking about the average change in temperature. Obviously, with climate change, there's going to be changes in the average, there's going to be changes in the fluctuations as well. I think there's a lot more work to be done here in terms of thinking about the effects of climate. But this, I think, is an interesting first look at how temperature could potentially impact outbreaks in this region, in these different places. So, we did all of that work for these different hypothetical scenarios in the United States. Then I started working with this group in Argentina who had questions about how climate might impact their work, and so, or about how it might impact dengue there. So this is work that I initially started doing with at least 4 people, and then since sort of the rest of the people up there have become involved in this project, and it's growing and growing, which is great. So we took that same model and we fit it to some data from Córdoba. At the time I did this, I only had the best data set we had was 2016. But the good news is we were able to get a model that looks relatively like the data. We didn't capture this peak here, but we did capture the trend and the timing of things. So that was good news. And that tends to line up here with the peak being in April. Most of the cases, most of the outbreaks in Córdoba have peaked, have been at their highest in April. Well, I would say that until the most recent outbreak.
It's like October, right? November.
Yes. Yeah, so it's the peaks tend to happen in their fall months, their autumn. I think there's a part of that is a human behavior thing. So I don't quite know what the holiday looks like here in Colombia, but in Argentina, the holiday is between summer vacation is between December and February. So a lot of people travel in that time. Carnival is also in February, so there's a lot of travel around that time as well. People come back, and then what we see is that the outbreaks often start around February and then peak in April. Sorry?
Usually, we expected summer or close to summer, but this is not start
Well, since if like in autumn, there is the autumnal cases, and then come to the vacations. Spring. For us, autumn, yes. But then it's spring.
But then it's all
I'm speaking about the New Year vacations.
in Argentina.
In Argentina, like before December, there might be no cases. Just in spring, and then summer travel vacations, and the cases will go up, but not that fast. And it reached the peak just in April, so it needs some time to develop the curve. Maybe that's the infections, the transmission starts during vacations, but it usually has delay or something. It accumulate sufficient cases. Any curve, you see, it begins very, very slowly growing and then steeper. It starts like December or January. In December there is nothing, and the months before there is nothing. So it needs some time to go and spread the infection. And maybe it's a thing.
Yeah, these are some of the things we're trying to figure out.
Well, April is also Holy Week. March or April. Another. And also, no.
But then only is because they finish the whole summer vacation and it's a long summer. Because here we have only 50 days in December, we need more, and the holiday for us is for them it's 2 months vacation, then
Yeah, one thing that I forgot to mention is that, at least in this part of Argentina, dengue is not being sustained through the winter. So these new outbreaks require a new introduction of dengue to happen sometime, usually we think between December, January, February.
June, July, August, it's peak winter there.
Yeah.
So there are some cases yet, but then the mosquito maybe die and the US will catch only when the temperature is warming up.
maybe the reason why this behavior in Córdoba because
All mosquitoes.
not all the infection. Some people go to do a data foundation and they was infected there and when they come back to Córdoba they are affected. Infection inside the Córdoba is after the infection. Maybe a little historical is
Yeah, one thing that I am working on doing is, right now we only have the data from Córdoba. What I would like to do is get the data for the entire country and see how the outbreaks in different places are lining up. eventually to do that with data from Brazil or Brazil, only in other cases.
Dengue is seasonal in Argentina.
Yeah.
But now we have also. Although it's going to take place more or less office. That's American.
Yeah. Oh, sorry.
I remember when I was doing the analysis, I might be wrong, I need to double check, but I think I found some, where I had like a suggestion of there's some interesting relationship when not only there was, when you have a dengue outbreak, you said normally you have some hot temperature before, right? But I think I had the observation that sometimes that's not the only thing. When you go even back, you have a really big cold thing. So you have like cold and then heat. So that interaction will also be worth looking at.
Okay, yeah.
And maybe that has to do with Sandra was telling me the incubation time of the eggs. Because sometimes she's a biologist, she knows her magnitude, that the mosquito eggs might even last
Here.
yeah, like months. They can
Yes.
see.
6 months.
So maybe these eggs that are in a really long period happen to coincide with those that were laid during a more warm period. So maybe those shorter and longer time periods coincide, and then you have a lot of
Did the entomologists from Argentina check the density of mosquitoes?
So,
This may answer some questions.
yeah, the data that we had
Density.
wasn't great for density.
On the other hand, it just occurred to me, so Mauricio did there was a delay like 5 months.
yes.
So in Argentina, it's getting warmer like in November, spring. So if you come from November to April,
Yeah.
5 months.
And I was also thinking with, I think there's some interesting dynamics with tourism because, well, I don't know how the Argentinian mind works, but I presume they would like to go somewhere far away when it's cold. They would like to go to like warm place to spend their winter. And maybe that coincides also with the introduction of the disease to the ecosystem. Because it will seem to line up, like they're returning from their trip with the 5 months gap that we see for the temperature rise. But like, I think it's a lot of factors that come together and unfortunately line up on this period where the pandemic is really big.
Yeah, it's all very interesting. It's, I'm trying to write that down. There are a lot of good thoughts about what could be happening here that I haven't necessarily thought of. I will say one thing that we are working on that I think this year, unfortunately there has been a very big dengue outbreak in Argentina. We have been collecting mosquito data since October of 2023 that is going to line up with the current outbreak, and we're also collecting temperature data. So I think it's going to be very interesting to look at all of that at the end of the season to see what relationships are there. And I think maybe it will help with some of these cases first. As I mentioned, the data we had initially was not great. So I think we're a little limited with what we can do with that, but we're very fortunate to get a grant to collect some data. So with that model, I asked the same question here about climate change. This I think is a little more interesting than some of the places we looked at in the US because in some ways, anyway. Of course, everything is a little flipped because now we're in the southern hemisphere, but this would be the current situation. So what we sort of know about temperature here is we would actually expect the cases that show up in October, November to lead to the biggest outbreaks based on what we know about the temperature relationships. That doesn't seem to be necessarily what's happening unless there is this long period of time between the introduction and the peak. But when we increase the temperature, at least initially, at 0.5 degrees Celsius, that really just increases the size of the outbreaks. With 1 degree Celsius, we see that the size of the outbreaks and then also a wider range. And then at 1.5 degrees Celsius, we've now suddenly gone from having this window of risk between October and February to being a year-round risk.
What is the lowest temperature in Portugal, in winter?
So this is from 2016, so
Like 10
about
degrees.
10 degrees.
But 10 degrees mosquito is not rich. Like 10 degrees. 10. Should be like 16, 17.
Yeah.
But the development time will be very long.
I think the earth is a very strong cycle. Mientras is más more hot.
Yeah. The development is faster when the temperature is high. But when the temperature is low, the development is very
It's the
slow.
earth.
Yes.
There's also something interesting.
Some level of saturation.
I think so. We see the outbreaks generally around February, March, right? And that happens to coincide when the temperature lowers. So somehow this temperature cycle also helps the outbreaks with slow down tracks.
Yeah.
Like
Yeah, it's difficult to disentangle that.
yeah, because this is what we spoke earlier. Some parameters happen to be correlated with temperature, but with a lag,
Yeah.
and some others not. For example, the action of the X, I will presume it is more related to the current temperature rather than the temperature 5 or 4 months back. While the, I don't know, the biting rate or something like that might be related past while it's in temperature.
Yeah. Yeah, it's complicated. So, with this particular model, and I should say I don't have time to go into the details of the small changes that we made, but in general, the model is very similar to the one that I described, except now we are including temperature in all of these different parameters in the model, and we've made it stochastic. So one question that comes up a lot when I show this figure is, well, that's deterministic. Like, what's happening when cases show up, like right here, right? Are they actually leading to outbreak, or are they dying off? Or, so the next question that we have, and these results that I'm going to show you are about a week old, so they're very new, are from a stochastic model where we implemented discrete time Markov chains, an approximation of the differential equations model. And we ran 1,000 simulations of the model for each of the different parameter sets that I'm about to show you. And we allow temperature to influence all of these things. So there's more than just 3 influences of temperature. We now have it in a lot of the other parameters as well. So we did the same thing. So I introduced one infectious person sometime in this period. I will say this, yeah, so this is January 1st. Apologize, my graduate student worked on these. Yeah, just by week. So the months aren't on there yet. As I said, these results are very new, but I was very excited about them. So this is week January 1st. This is by week of introduction after that. And so now what we're looking at is the actual probability of having local transmission, which is just one case, depending on that time of introduction. So one thing to notice here is that the highest probability of actually having local transmission is occurring sometime, generally, it's at its very highest right here, but generally for this period here, between late February and early April. So that's the time in which we would expect have the highest probability that when a case comes in, a mosquito bites that infectious person and successfully bites another person. So that is one result here. She also looked at sort of the probability that an introduction leads to case outbreaks of different sizes, but I don't have that figure, unfortunately. The other thing here is that the local transmission is very, very low now during this time period. So those introductions, I'm going to flip back for a second, that we were seeing sort of down here, August, September, October. Now here, it's basically zero. So we're not really expecting to see those introductions lead to outbreaks at all. And then that actually quite sharply goes down here as things get infectious. We also looked at the peak size. So when an introduction occurs sometime in late February, that's when we would see the largest outbreaks, which potentially lines up with what we're seeing in terms of the timing of cases coming in. So even though the outbreak itself may peak in April, it's maybe starting with cases that show up in February. And the outbreaks that begin in February also tend to last the longest. So these outbreaks that are starting in February are lasting maybe up to 20 weeks before they're completely gone. And some of those are just outbreaks where just a few people are infected late into the year, but then some of them are where we have peaks and then things die off pretty quickly. The other thing that I don't sort of really point out here though is that even some of these outbreaks, so this, I should say, both of these are now conditioned on transmission actually happening. So this is a smaller subset of our samples than the previous figure, in the sense that these are outbreaks that occurred, but it's only for the situations where we actually had local transmission. So the zeros aren't. So this is something that is very, very new. We're very excited about this. She is now running the simulations for climate change, so I don't have those to show you, but we are moving, I think, in a really cool direction with this. So I have some general caveats to all of this work. We've completely ignored precipitation and humidity, which we at least know humidity can be important. Precipitation tends to not show up as important, but seems like it should be important. And so I do actually have some undergraduate students who are working on a precipitation and humidity model, just because it's something that I think we're interested in looking at. This relates to Mauricio's question earlier. All of the temperature that I've included in the model assumes an instant impact. So the temperature today determines the lifespan today. We do that because delay differential equations are no fun, but we are working now on thinking about delay differential equations, thinking about distributions of delays, and finding ways to, there's actually some really cool work in the insect entomological modeling world where they look at degree day models, where I'm sure you probably all know about this, but they're very new to me, so I'm very excited. Where they look kind of to see how temperature impacts an insect over its lifespan. And so I think that would be really interesting to include in these models. But unfortunately, harder to simulate.
I think la idea to model the impact of precipitation, we need to put another variables like socioeconomic variables. Because if you have precipitation and you have water system at home, you don't need to save water in storage, right? Yeah. And maybe in some area, in the same precipitation, you have 2 or 3 different kind of social development. And sometimes in some areas you don't store water when you don't have precipitation. Yeah.
the case.
I know as well.
Another thing here is the data we had is collected across some heterogeneous environments. This is actually related, I think, more to the results that I'm not showing you about the models, but ignore that last one. A couple of conclusions here. So temperature, we think, is an important driver, a good predictor for dengue transmission in a lot of places. Seasonal temperature can, it seems like, play a very significant role in whether we have outbreaks and the potential for outbreaks. These fluctuations have a very big impact on a lot of these metrics, like vector lifespan, incubation period, transmission, and at least from our initial results, things warming up is largely bad news for a lot of places, especially places that are temperate. Just briefly, I wanted to talk about where we're going with some of this. So this is my collaborator, Elias Dayo, who's at CONICET. About a year and a half ago, we won an award from the Borough's Wellcome Fund to fund specifically studies of dengue and climate in Cordoba. And so what we are working on now is collecting a lot of longitudinal data on climate, mosquito populations, and dengue cases in Cordoba, the city, and in Villa Carlos Paz, which is a small city outside of Cordoba. And we have this really cool citizen science project going on where we're working with high schools and high school students who are helping us with the data collection. So they're taking traps to their houses and putting them in their houses. They bring us back the traps with eggs in them. Our core lab, our graduate student and then postdoc, and our lab assistants count the eggs on the microscope. And we're doing this at 150 locations in total across all the schools. And it's going really well, and I think the students are really excited about it. I'll share the paper, the story that I shared earlier about the project and about what the students are doing. This has been a really great way to sort of also incorporate the community a little bit into the work. Especially, and we obviously didn't time it this way, but it's been especially good this year because as dengue has been such a big problem, we started working with the students back in September before that was the case, and so I think it's been nice for them to kind of learn about what's happening as they're sort of going through a very big outbreak. This is one thing that I'm thinking about in terms of modeling, and then also thinking about expanding the modeling to include precipitation and humidity. That's what my undergraduates are working on now. They've done a lot of really good work with it. It's not quite ready to show yet, but I'm happy with where they've gone with the precipitation models. And just sort of finally, I'm working with this other group in the Dominican Republic, and some of the interesting things here have been slight differences of what we're seeing in endemic regions versus emergent regions. But largely, we are able to use a lot of what we know is happening in the endemic environments to tell us about what's happening in the emerging regions. And I think this is also the case in Colombia, but I have this data set in front of me. So in the Dominican Republic, dengue has been around for a long time. There has been a huge increase, and actually what's not shown here is everything after 2018. Where 2019 was a very big outbreak, much bigger than what we see here, and the last 2 years have been bad as well. So even though it's been around for a long time, it seems to be getting worse and worse and worse. So we're learning a lot, actually learning a lot about what's happening there too from what we're doing in the emerging area. So it's kind of been a nice exchange. I just want to thank everybody else again who was involved in this project. And this work has been funded by a lot of different sources. We have our BWF grant, which has been great. Something maybe just to put on everybody's radar here are these two opportunities. So the Inter-American Institute for Global Change Research has some very small grants to help fund projects. They usually come through very specific funding calls, but part of our Cordoba work has been funded by that. And then there's this Global South Artificial Intelligence for Pandemic and Epidemic Preparedness grant. It's actually comes out of York University in Canada. So the Dominican Republic work is now funded partially on that. I am not really doing AI, but I think sometimes when they say AI, they just mean modeling, statistics. So we are working on models and statistical models for that work. But that is something, I don't know when they're going to do another call, but it might be something that would be very good for this group as well. These are a lot of papers that were published related to this. I'll stop there. I do have other stuff that I can talk about, but I've kept you for like over an hour now, so thank you.
Víctor.
Yes, I can do that.
This one.
Yes.
Ya de un trabajo de doctorado tú has hecho algo similar y parece coherente con lo que tú has hecho, ¿no recuerdas?
Sí, algunos. Sí, algunos. Hay otros que la curva a veces llegaba a bajar y lo que descubría creo que era la oposición. Pero en general sí, con las temperaturas.
Pero tú has usado otros polinomios que eran como de grado 4
y había unos de por eso digo que hay unos donde tienen mayor oscilación porque había unos como de grado 7.
Pero tú has usado las temperaturas.
Las medias de acá. Lo que hicimos fue usar un experimento que habían hecho en Brasil con temperatura controlada. Y ellos tenían los coeficientes para los polinomios, entonces uno utilizaba la temperatura media de acá para hacer la estimación. Eso está en un artículo que nosotros hicimos. Y ahí está, porque hay hasta una corrección en uno de los ajustes comparado con el que habían hecho.
Ella también.
Sí.
Yo simplemente quería ver, a mí me gustó
Sí, la sí.
So zero, I think T0 to be at TN minimum and maximum for the range. So like, I think for instance, this would T0 maybe 15-ish, and this would TN like 35-ish.
The maximum or the thing that is positive and what's the minimum.
Yeah. And I should say not all of these are.
square root.
Yeah. So you would estimate all three of these, C, T0, and Tm.
Maybe, well, Mauricio.
Okay, you look at where you have the, I think it's some sites, right? Alpha level. Where you have some, there. There was the one that I was talking about. Sometimes you have the big divided deviation for hot temperature, but then previously, like during this, you have the big spike down. So that might just be like in nature, like it said, like temporal taxonomy. But I remember something, seeing something like this when I was in my office. Maybe there's this relation. Maybe we're talking about with the first the impact on the dynamic relation, the relation dynamics, and then a more instant or instantaneous effect on the day-to-day in this graph, I kind of suggest that idea.
Yeah. Think of the cooler period here, here. Here's a little far
Yeah,
away.
but it doesn't have the hot spike after.
Yeah.
Maybe I don't know. It's just an idea. Let's say. And I'm particularly interested also on the way you feed these curves for the different parameters, like red and so on. Would you say that those would be hyperbolized enough that you were to do something similar here at your hydrophilic binding? Will those vary from the results you're getting at Argentina or let's say where there is a strong personality?
Question. Something that would be interested in sort of investigating. Putting people with quantitative involvement.
Yeah.
Or are you just thinking in terms of the like these relationships here? Yeah.
Well, not only this, of course, these are.
Accumulating basically production number, it's so very interesting.
Yeah.
Maybe we can do it like an indicator. It's kind of indicator. Over bucket.
Instead of incidents,
Without one bucket, with one bucket.
instead of incidents.
We usually do accumulate incidents. Show without one bucket, with one bucket. Yes. It's indicator.
Also, we were interested for our future work on characterizing the uncertainty of those parameters. There have been some previous work where this probability distribution has been assumed to be constant. But we think that might not be the case, and you've shown those graphs. So we are interested in constructing something similar, but we want to have in consideration the tropical climate. That's why I was asking if there will be differences on those results based on where you are taking the data. I'm not quite sure it's not an equal effect because at the end of the day you are just considering temperature. And here we have a smaller range of variability on minimum and maximum temperature. Maybe the perfect balance, I guess. So we'll really be interested in understanding more of how you construct those curves, how you can construct data. That will make some future work for us.
Yeah, so the way that I didn't fit these. Those are all in the paper. These I fit actually basically But I think there are ways that we can look at those relationships in different climates. And I don't have the figure for something, but where we can look at what all of those, that whole panel relationships look like for a year for one location. So, yeah. Hiding in a chat conversation with my graduate students. That's the only place I have it. But basically where we take all of these relationships here and we look and see, instead of looking at the versus temperature, we look at like across the year elevation. And so I think that would be something that would be interesting to look at for the tropical climates versus the temperate climates, just to see how much difference there really is in each one of these, and see if you can ask a question about how much each one of those things might contribute differently in different climates. So, do all of these things matter the same in a tropical versus a temperate climate, or is one of them more important in a tropical climate versus a temperate climate? Yeah, I'd definitely be happy to talk to you all about that and do something with all this.
Yeah, I think I should really read the article you were saying, because it really seems to be the missing piece that we are looking for.
Yeah, I can send you everything.
And speaking of this cumulative basic reproductive number, have you published any papers on that? Just to see how you calculate. So I mentioned that you do it by generations. You count the infectious period, and then probability of still coming to infect, and then to pass. So how do you estimate the number?
So the way we did it for this was we did it completely numerically.
Well, of course, numerical.
So what we did here is we just counted the cumulative number of cases that occurred within 1 year of introduction, and that's our what we're showing there is the cumulative number.
But then you just divide it by periods. Maybe during the first month there were very few cases, and the next month it's a huge number of cases.
Yeah.
You just the average.
Yeah.
Like that. So you have 1 month, let's say 50 cases. Another month you have 500 cases. So you accumulate 2 cases. So for 2 months you do like 550. So on average per day it's 550 divided by 60 days.
Oh.
That's like that.
Yeah, that would basically be that.
Okay. But it's kind of looks different.
Yeah, it does look
Yes,
different,
yes,
yeah.
yes.
Because
Yes.
if you try to recover the population number,
We usually construct like
yeah, but
effective reproductive number. So
remember the number
going
of
back here, we can use this.
remember the number of the population that they have difficult to
just normal basic reproductive sample for electrical disease.
Two guys are in partner in Argentina, Córdoba, is collecting information. Our problem is that we are collecting information. The electrical system is collecting weekend. The temperature we have all day. But now, we are in the group.
Yeah, we have, well, we had hoped to have meteorological stations collecting data with edge in schools. International bureaucracy got in the way, but
yes, you have the electrical weather stations, but the quantity of eggs, mosquitoes, everything, in order to relate with this temperature and with the emergency information.
we should finish the data collection. And happy if people want to contact me, Ola has my information. I have some more information. One reason I went counts to work with people, so that would be great. We can make that.
Very effective topic for me now.
But they are also best.
Yes. There are a lot of questions. So many more create and analyze and publish. Okay. Now we need adapt.
Yes.
¿Qué andan? ¿Qué es lo que quiere hacer usted?
Pues, aquí.
Bueno.
Recién conmigo.
Leo y escribo mucho emails.
Sí, pero no nos pusimos de acuerdo.
No hace falta ponernos de acuerdo.
Así yo no pedí, yo estaba siempre así, no me obligar.
¿Cómo que bailar? ¿Alcanzó a ir a Panamericana?
Sí.
No, ella alcanza a ir a
Alcanza a ir, pero no va a volver.